Here we're going to look at a little bit more formal way to evaluate limits rather than just using graphs and tables, but graphs and tables are very useful in some situations. But this first statement says that essentially when we're trying to evaluate limits of our basic elementary functions, meaning our power functions, our radicals, sine, cosine, logarithm, etc. So those basic functions that we named as kind of those that we'll be using throughout the course. Then it turns out evaluating limits is pretty easy for the most part. If you want to calculate the limit as x approaches a of f of x, it will equal f of a as long as f of a is defined. I mean, you can't, for example, plug in pi over 2 in tangent because tangent of pi over 2 is not defined. So it's kind of assuming that this statement makes sense. So things like the limit as x approaches 1 of natural log of x. This is claiming as long as natural log of 1 makes sense, I should get natural log of 1, which we remember to be 0. And sort of to justify this, here's natural log's graph. And all this is saying is that when I come into 1 from either side, I can see that my graph is not going to do something weird from both sides. Our functions, our basic functions, are defined nice and smoothly so that they match up in places where they're defined. As I mentioned with the tangent, I can't do this one by just plugging in. If I want to go to pi over 2, say let's go from the left of tangent, that one is not going to equal tangent of pi over 2 because tangent of pi over 2 is not defined. And we can see what the problem is. Here at pi over 2, if I'm coming in, tangent looks something like this. And so in that case, we have to look at the graph and we say, well, if you're coming in from the left, this would actually equal positive infinity, or not equal, but we define it to be positive infinity. So be sure to read that definition or that note with a little bit of a little bit more than what's stated there. Everything has to make sense. So all of our basic functions, I just, for the most part, plug in. As long as it's not some weird thing going on and I'm hitting a place that's not a domain or something like that. So in this case, we get 4, because you're just going to have 2 squared. If I take the limit as x approaches 5 of the constant function 3. Well, constant functions, there's no place to plug the x in, so every value is going to be 3, no matter what you approach for a constant function. And if you just think about the underlying graphs in all these cases, there's nothing weird going on here, there's nothing weird going on here, so on. Works for trig functions, limit as x goes to pi over 2. For sine, that one makes sense. That's sine of pi over 2. And you may recall that that's 1. You can do it for inverse trig functions and exponentials. So let's take the limit as x goes to 0 of e to the x. Well, that's going to be e to the 0, which is defined, and that's 1. And say limit as x goes to pi over 4 of tangent inverse. Not pi over 4, giving away the answer. Limit as x goes to 1 of tangent inverse is, as long as this makes sense, it's tangent inverse of 1, and you have to think of the graph of tangent inverse. Kind of this sideways tangent going on here. And if I'm coming out here to 1, I'm trying to figure out the y coordinate of that point, which, using a little bit of trig, the way I would read this is the inverse functions give you back the angle. The trig functions take the angle to a number. The inverse trig functions take that number back to an angle. And so I rewrite this as I want to know when tangent of theta is equal to 1. That's equivalent to stating that. And there's several ways to do that. You can draw triangles. You can use the circular function if that's what you've memorized. I'll use triangles mostly in here. This in a triangle is defined to be the opposite over adjacent in a right triangle. So if I have my angle theta here in this right triangle, the opposite and the adjacent together need to give me 1. So I'll just put 1 and 1 there. And then if I use Pythagorean theorem, this is square root of 2. And I recognize this as a 45, 45, 90 triangle. So theta would be 45 degrees, but in calculus we use radians. So that would be pi over 4 would be this limit. Like I said, I was giving away the answer when I wrote it down. So a lot of this is just a matter of evaluating functions when you just have your basic functions. But we can also up this to combinations of basic functions. That's what this theorem is saying. So I've got two functions that are defined except possibly at some number a, and that's the value I'm going to approach. I'm going to let x approach a, and maybe they're not defined there. That's okay, because we know that limits don't have to be defined at a. And so what I was doing above when I said it didn't work for tangent was because that not only was it not defined, it was going to infinity. But if I just have a little break in my graph, then I can still do the limit. And that's what this is saying. So maybe they're not defined at a, but the limit as x approaches a of f is L, and the limit as x approaches a, that's supposed to just be a g there, sorry, typo. And the limit as x approaches a of g is some m value. So there could be a hole in the graph. So, my graph f could be coming here and doing this as I approach a, but it's giving me the value L. Doesn't have to be defined there, we know that. That's where the graph is going. And then it says the following will be true, that if you multiply your function by something, and then take the limit, you can take that constant out of the way, and it'll end up being multiplied by whatever the limit was. So, for example, if I want to take the limit as x approaches pi over 2 of 3 sine x, well, above we said that's just, if you're just doing sine x, that's sine of pi over 2, but we didn't say you could do it with a 3 in front. Well, it turns out what this statement 1 says is you can take the 3 out of the way and take the limit as x approaches pi over 2 of sine x. So the constant comes out in some sense. And so then I get sine of pi over 2, which is 1. And so this ends up being 3 times that limit being 1, so the overall result is 3. So it gives us a way to expand. Every one of my basic functions can have some constant in front. And you can ignore that constant and put it in at the end. Not really getting rid of it, you're just pulling it out. Likewise, if you're adding the two functions together and taking their limit, you can take the limit separately. Sometimes this is stated as being the limit of the sum is the sum of the limits, and you end up with the answer being the sum. So now that allows me to expand things like taking the limit as x approaches, don't want to beat this one to death, but say I've got x plus sine x. That's going to be pi over 2. In other words, I don't have to show this step every time that I'm going to break it up. I just take the limit of that and the limit of that separately. So I get pi over 2 from that first one, and I get sine of pi over 2 from the second one. And so that would be the limit of that sum. You just do each limit separately. There's no special rule you have to apply, which is nice. That's not the case in every other operation we do in mathematics. A simple example would be square root of x squared plus 1. That is not the square root of x squared plus the square root of 1. Be nice, it would solve a lot of problems for making, when people try to simplify this, but this is not true. But it does work for limits, adding or subtracting, and it turns out this says it also works for multiplication. So in a similar way, if I take the limit as x approaches pi over 2 of x over sine x, I just take the limits separately. I take the limit as x approaches pi over 2 of x, and the limit as x approaches pi over 2 of sine. And what I get is, in the top, that's just pi over 2. In the bottom, it's sine of pi over 2, which is 1. So the answer is pi over 2. I would have a problem if that denominator turned out to be 0. So, for example, if I were trying to do cosine here instead, then I couldn't take this limit in the denominator like that, because cosine leads to 0. So you can't say this equals, the limit of a quotient is not the quotient of the limits in that instance. So keep that in mind. That turns out to be the one that's going to give us our most work when we're actually evaluating limits. So most of the time they're not going to be this easy where you just plug things in. Most of the time we're going to have to do some work to figure out, oh, I got a 0 here, and what do I do with it? And then the last one there is just saying, here's the other combination if you have a composition of functions. So that allows me to take things like limit as x approaches 0 of the square root of x squared plus 1. You could have further compositions than just 2. But this says that, in a sense, that the limit goes all the way to the inside. So technically, here's what I'm doing. Limit as x goes to 0 of x squared plus 1. And then I take that limit and take f of that. In this case, the f is my square root. So this would be the square root of 0 squared plus 1, which is 1, and the square root of 1 is 1. So compositions work. The only issue that I didn't address here is, what about the limit as x approaches 0 of the square root of x? You would say, well, what you said above, you just plug it in, and that's true, you end up getting 0, but technically this limit's not defined as is, because when you look at the square root of x, it looks like this. And remember, when I write this limit down, I'm saying that the limit from this side and this side are equal. Well, this side doesn't make any sense. So technically, I can only do this limit from the right. But a lot of times we leave that little bit of that subtlety out, and we don't put the from the right on there. But technically, this limit only exists from the right, even though sometimes we do write this when we're not being totally careful. But if we want to be careful, we'd want to put the little plus sign. But that gives us a quick way to evaluate a whole lot of limits. Essentially, we're just plugging in the value that we're approaching.